resistance. Okay. So for discrete domain, okay, it consists of only certain number in interval. So let's say 1 to 5. Okay, computer signals with the example. Okay, so if 1 to 5 means that you only hold the number 1, 2, 3, 4, 5. Okay, you don't have the number in between it. Okay, so this is the discrete domain. Okay, so what is sequence and series? Okay, so sequence, a list of number in order. Okay, each number in sequence we call it a term lah. So you can see it start from -2, -1, 0, 1, 2. Okay, this is sequence. Okay, it is in order. Okay, for notation, if for a notation like this, the F indicate the terms and the K indicates the terms number. Okay, so like for example, this is the first term, second term, third term, fourth term, fifth term. So if you're talking about F5, will be this term. Okay, so the K can be from negative to infinite. Okay, or they can give you a certain number lah. Okay, it depends on the questions or the conditions. Okay, for sequence, if a sequence has infinite numbers of elements, it called an infinite sequence. Okay, otherwise it will be finite sequence. So infinite sequence, we can start from negative infinite to infinity. Okay, so if you're right, you want to write this sequence out. Okay, it will be start with dot 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 because you're not sure from where it starts because it is negative infinity. Okay, okay, so from xk, you will know is the k terms. Okay, while the k starting from negative infinity to infinity. So we start from dot 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 dot. Okay, and certain number we start at -2, let's say. Okay, to 2. Okay, but after 2, you still have numbers. So just put dot 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 lah. Okay, so it will be negative infinity to infinity. Okay, but it can also be you have one of the numbers. Okay, starting from -2. Okay, starting from -2 and to infinity. So your sequence, okay, you can start from -2, -1, 0, 1, 2, and so on. Okay, so you cannot finish it, cannot finish writing everything out, so you just put dot dot dot. Okay, but for finite sequence, it will be starting and ending with end with certain value, certain numbers lah. Okay, so the first number will be 1 for here. Okay, and end with 10. So it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 until the last one, 10. Okay. Okay, so I think this one very straightforward lah. Right. So type of sequence. Okay, let's HK equals to 0 or 1. So when it's 0, the K equals to -1, -2, and etc. Okay, so -1 is here, right? -2 is smaller than -1, and etc. So we will be keep counting, right? To this, to the left side. Okay, so means that to the left side all will be holding a number of 0 lah. Okay, so for 1, it start from 0, 1, 2, and to infinity. So 0, 1, 2 to infinity. Okay, so this is a discrete number. Okay, discrete time, discrete number. Okay, and the sequence followed by this given statement or the given equation. Okay, so this one we call it unit step sequence. Okay, we know the unit step start from 0 and then 1 here, right? Okay, so or it can be delta k. Okay, the given is delta k, and then they say 0 when k is not equals to 0. Okay, what mean by not equals to 0? -1 not equals to 0, -2 not equals to 0, 1, 2, 3 also not equals to 0. Okay, the only condition is when it is 1, when k is equals to 0. So when k is equals to 0, it is 1. Okay, so this one, okay, these conditions, this type of sequence, okay, it will be written in lambda. Okay, we written in lambda, and this one we call it unit pulse sequence. Okay, it's only one pulse. Okay, unit pulse sequence. only here. Okay. Okay, so take note, we have unit step sequence and unit pulse sequence. Okay, but normally we will be working with unit steps. Okay. Okay, so a sequence is said to be causal if xk equals to 0. Okay, what is causal? Causal means that it is 0 before n is equal to 0. Later, you will see the conditions. Okay, so both unit steps and impulse sequence are causal. Okay, so you can see when this at the negative side, it will be 0. Okay, it will only start from 0 to the right side. Okay. Okay, note that, okay, xk can be sequence. Okay, while if you use xk multiplied by hk is unit step sequence. Okay, so hk is unit step sequence. Okay, then these two you multiply together, right? So it will combine. Okay, it will be causal. Okay, so causal means that only after 0. Yeah. Okay. Okay, so throughout this topic, we assume causal sequence unless otherwise specified. Okay, so k will be equals or more than 0. Okay, like I said, equal or more than 0. Equals or more than 0. Okay. Okay, so if you have problem, you can ask, yeah?
Teacher,
Yes.
I have a problem. The
I
square,
can't hear you.
it's about the part that's like like square something like that, but infinite, basically powered by infinite, and the bottom part of the k equals negative infinite. I
It's
was
not a
confused.
square, it's a limit. It's a maximum number and the minimum number.
Oh, it's maximum and minimum.
Okay, yeah. Okay, you can refer back to this part. Okay, we start from -2, so we count from -2 and then until
Oh,
infinite. Okay, or we start from 1, then we count to 10. Okay,
oh. Then the k is represent for the number.
yeah, the index.
Oh, okay, understood.
Okay, okay, then we proceed to series. Okay, define what is series. Series defined as the sum of sequence where the order of element does not matter. Okay, it doesn't matter of the uh, orders. Okay, so the list of number with the addition operations in between finite series and infinite series depends on the type of sequence, whether it is finite or infinite. Okay, so for example, 1 plus 3 plus 5 plus 7 is an infinite series. Okay, because you didn't know when it will stop. Okay, so this is the written notation. Okay, so you guys can jot down a note. So this S is the sum. Okay, it's sum of the MK lah. Okay, so this symbol is a sigma. Okay, sigma, SIGMA. Okay, sigma means that to add up everything. Okay, it's to the sum of lah. All right. So the k equals to 0 means that we're starting from the first term. Okay, so the k is the value corresponding to this index k. Okay, so you have um, from the first terms to don't know how many terms lah. Okay, written here. Okay, so of course over here they put an infinity. Okay, so means that it is infinite series. Okay, so for this one you can also written in this way: sum equals to m0 plus m1 plus m2 plus M3 plus so on. Okay. You can write as sum equals to M1 plus M2 plus M3 plus M4 plus dot dot dot. Okay. Okay. So this is what this mean by. Okay. Okay, so there's a bit difference of sequence and series lah. For sequence, the organizations of term in particular orders. Okay, you have orders. Okay, series, the submissions of term. Okay, is a submissions of terms. Okay, you can see the plus sign. So for sequence, order of the term is most important lah. So A sequence 5, 6, 7 is different from 7, 6, 5 because we don't know what is the patterns behind, right? So we will be following the sequence. Okay. So in this case, if the sequence can be 1, 2, 3, 4, 5, 6, okay, then you can write in this way. Okay, they're starting from k equals to certain number. So for this sequence, it will be k equals to 1 lah. Okay, k equals to 1 until infinite. Okay. Okay, so for series, it will be at summations. Okay, a series of number, a summations. Okay, it's a sum. Okay, so in this case, the k, this is k0. Okay, this is 0, 1, 2, 3, 4, 5. Okay, so this is k0, k equals to 0 until k equals to 5. Okay, but we're not sure what or when it will end lah because it's a infinite series. Okay, so this is a difference of sequence and series. Okay, sequence is every terms. Okay, you arrange every terms in orders. Okay, in certain orders or in certain patterns. Okay, for series is like the summation. It will be like adding up everything. Okay, adding up everything, every numbers that is listed. Okay, clear? Okay, if okay, we go through the topics for today's Z transform. All right. Okay, what is Z transform? Okay, Z transform is to convert discrete time signal, which is sequence of a real or complex number, into complex frequency domain representations. Okay, so this one normally you'll be using in those electrical subject. Okay, with signals and all that, signal processing and all that. Okay. Okay, so but now what you need to know is how to do the Z transform. Okay, so this part you can learn it afterwards. Okay, now you only need to know that when the question is given, how you do the Z transform. Okay, so a discrete time equivalent of the Laplace transform. Okay, it's a little bit similar like Laplace transform, or I can say even easier than Laplace transform. Okay, yeah, later we'll see. Okay, so basically you have a formulas to reverse also. Okay, there will be six, I think 5 to 6 given theorems to reverse, right? Okay, so the Z transform of the causal sequence. Okay, so this is the sequence given, right? Xk. So just now we have seen xk. Okay, we represent the sequence with xk. Okay, it's denoted by this. Okay, Z transform, of course, you put this Z here lah. Okay, Laplace transform, you put an L, right? So Z transform is a Z here. Okay, then we know that it's a causal sequence. Okay, causal sequence means that k equals to 0. We start from the k equals to 0. Okay, to infinite. Okay, so or xz, okay, is defined by this. Okay, so you don't need to understand how this come out lah, right? So what you need to know is the way, okay, we do the Z transform. Okay, so after you do the Z transform, you'll get these complex numbers here. Okay, where Z, okay, is C, okay, provided the sum exists, k is an integer in a positive index. Okay, so because it's causal, right? It's causal means that it will be positive. Okay, so then we can straight away look at the, okay, I skip this part first. Okay, then you can see there's, this is the theorem. Okay, one theorem, two theorem, three, four, five, actually. Okay, but of course certain conditions might give you this. Okay, so because if z, if this is equals to 1, then z minus 1. Okay, if it is a, then z minus a. Okay, so these are the a few theorems for z transform. Okay, we go back to this first. Okay, so for example, this is the given sequence. Okay, so this is a given sequence. Okay, x k. Okay, you don't know how many k you have, but you have start from the first term. This one k equals to 0. Okay, and to infinite. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, blah, 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 blah. Okay, so this is actually a repeating sequence. You can see, right? 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. Okay, but it is arranged in orders, right? This is, if you count with orders, the first term, second term, third, fourth, the fifth term, 6, 7, 8, 9, 10, 11, 12 terms, right? So, okay, so if I want to do Z transform for this, okay, which is carrying this term, okay, how I do it? Okay, so by referring to these theorems here, okay, so we do the transform and it will be a summations of xk over the zk. Okay, xk, this xk is these terms, right? This term. Okay, or this term is the xk. Okay, zk will be z to the power of the number of the terms. Okay, so this one, the terms, you're starting from 0, 1, 2, 3, 4, 5, 6, right? So then you can see, then they can rewrite it in this way. So 0, 1, 2, 3, 4, 5, 6, okay, is the numerator, right? I mean the terms are, so the first term 0, okay, 1, 2, 3, and then followed by 0, 1, 2, 3, and of course you should have so on like 0, 1, 2, 3 again. Okay, and the bottom part, the denominator will be z to the power of the 0 terms, 1, 2, 3, 4, 5, 6, 7, and so on. Okay, okay, everyone can get this line. Okay, okay, then you can find out that they have all different denominators, right? But if you rearrange it, you can get the same, the terms with same denominator to put it together. Okay, of course, this one will be 0 lah. This one will be cancelled off because 0 divided by any numbers also will become 0. Then you left with terms with numerator of 1, 2, and 3, right? Numerator with 1, 2, and 3. So then you can group them. Okay, so you can group them 1 over z, okay, and 1 over z to the power of 5, and so on. 2 over z squared, 2 over z to the power of 6, 3 over z cubed, 3 over z to the power of 7, and so on. Okay, then this one you can group them. Okay, okay, then after you group them, okay, you can factorize it. Okay, if you factorize it, okay, this is what you get. So bring out 1 over z, you bring out 2 over z squared, you bring out 3 over z cubed. Okay, then you find out that this part, and this part, they are the same. Okay, so you can put these three terms together. Okay, okay, so these three terms multiply to by this. Okay, okay, so for this one, then you can simplify it. Okay, this is a math question lah, right? Then you can simplify it, and then for this, sum of infinite series, okay, you can apply this theorem. Okay, so this one also a fixed theorems. Okay, when you have this sum in infinite series, okay, you can apply this term. So how we look at this term, A, okay, the summations of this series, okay, equals to A1 over 1 minus R. So A1 is the first term, okay, when you have a one small one here, means that it is a first term, okay, the first term on top. So now in this sequence, the first term is 1. So put 1 here, okay, over 1 minus R, over 1 minus R, okay. So the R is actually the common ratio, okay, the common ratio. So in this case, the common ratio will be 1 over z to the power of 4, okay. So 1 over z to the power of 4, then they just put in, and then they'll just simplify it, okay, then you'll get this answer for this question, okay. Okay, so this part, but no worry, this is not the usual questions that you need to answer. Okay, this is just to tell you that for repeating sequence, okay, okay, you can solve it in these techniques. Okay, what 3p? What do you mean by 3p, Wilbur? You having question? No question. Oh, okay. Okay, then we go through the theorems, okay? So now take a photo of this, okay, or screenshot this, okay? So when you solve the Z transform, you need all these theorem, okay? Okay, just like your Laplace transform, inverse Laplace transform, and everything, okay? You need this, okay? Okay, then we look at the first question. Yeah, I'll briefly go through lah. Okay, if you do Z transform of the delta K, it will be equals to 1. Okay, because it's impulse sequence. Remember, just now we seen that it's just a pulse. Okay, it's just a pulse, so you get a 1 lah. Okay, if you do Z transform of A to the power of K, it will be Z over Z minus this power. Sorry, the A. Okay, okay. So in particular, putting A equals to 1 lah. Okay, so if A equals to 1, okay, Z1 lah. So Z transform of 1, you get Z over Z minus 1. Okay, so if you do this Z transform with K minus 1, okay, with a coefficient K and K minus 1, it will be Z over Z minus A square. Okay. In particular, we're putting A equals to 1. Okay. So when A equals to 1, everything equals to 1, means that you are actually doing Z transform of a K. It will be Z over Z minus 1 square. Okay. Or if you are doing Z transform for cos and sine, okay, you will get this. Okay, this one you just memorize it. Okay, trust me, you just memorize it. Okay, you won't be able to derive it in the exam. Okay. Okay, if you get cos AK, then that's it. Okay, if you get sine AK, that's it. Okay, of course, if you have other coefficient, you just bring it out. Okay, just factorize it out. Okay. Okay, then we go through. Okay, so this proof, we just skip it lah. Okay. All we given or some yeah, some you need to memorize. Okay. Sorry for late, but I'll give you the all the formula list by this week. Okay, you'll just refer and check which one is not given. Okay. Okay, so for the proof, we are not going through it lah. Okay. So basically, for the delta for this unit pulse, it will be equivalent to 1. Okay. Okay, for this one, it will be, okay, you just remember this lah. Okay, you don't need to remember all this proof. Okay. Okay. So I'll just skip these two slides for proof. Okay. When you're doing revision also, you don't need to really go through this lah. Okay. Then we look at some simple example. Okay, so we have copied all the theorems here. Okay, so we just try out lah. Okay, so Z transform of cos 2k. Okay, so this is what you need to refer, right? So 2 is A lah. So A equals to 2. Okay, so now you know A equals to 2. So you just copy Z bracket Z minus cos A, right? Cos A. So A is 2 here. And over Z square minus 2Z cos cos A, right? So A equals to 2. So 2, okay, plus 1. Okay, so how you see Z more than 1, okay, because of this, okay? Z is more than 1 in this case, okay? So unless you get cases like this, when Z is more than A, so you just identify what is your A lah, then you just put in, okay? Okay, so for cos and sine, it will be Z more than 1. Okay, so for sine, okay, so this one, the A is pi over 2, right? A is pi over 2. A equals, A equals to pi over 2. Okay, you just write out A equals to pi over 2. Then it's sine, right? So this one. Okay, so just put Z sine A. So Z sine pi over 2 over Z squared minus 2Z cos pi over 2 plus 1. Okay, so in this case, pi over 2 will be 90 degree lah, right? Then you use your calculator to simplify it. Okay, so Z pi over 2, sine pi over 2 equals to 1. Okay, cos pi over 2 equals to 0. So 0 multiplied by this term, the whole terms will be 0. Okay, so at the end, you're left with a Z over Z squared plus 1. Okay. Okay, next. Okay, Z transform of 3 to the power of k. Okay, so this is the term, right? A, k. Okay, so Z over Z minus 3. Your A is 3. Okay, and for the condition, Z is more than 3. Okay. Okay, following by the next example, Z, okay, negative 1 over 2k. Okay, so in this case, it's still this condition, right? So your A is negative 1 over 5. Okay, so equals to Z over Z minus negative 1 over 5. So it'll be Z plus 1 over 5. Okay, then you just rearrange it, you will get 5Z over 5Z plus 1. Okay, but this is your final answer, right? But your terms here, not Z more than 5. Okay, Z is more than A. So your A is negative 1 over 5. Okay, so absolute of A will be 1 over 5. Okay, so take note of this part. Okay. Okay, not. All right, then we can proceed to these last examples here. Z transform of K to the power of K minus 1. So it will be this. All right, now. Okay, so in this case, A equals to 2. Okay, so z over z minus 2 square. Okay, z over z minus 2 square, the whole thing. Okay, so z is more than 2. Okay, your a is 2. So z is more than 2. Okay. Okay, so far so good. Until here. Okay. Okay, then we go through the property of Z transform. So property of Z transform also similar to Laplace transform. Okay, so they have the linear properties, shift properties, and multiplying property. Okay. So first we go through a linear property. Okay, linear property. Okay, you look at the theorems here. So for Z transform, if you have alpha multiplied by Z xk, beta multiplied by yk, okay, so you can actually put the assume, okay, they are the linear properties, right? So you can just Z transform this plus Z transform this. Okay, so when you separate it out, you will get Z transform alpha xk plus Z transform beta y, sorry, k. Okay? Okay, then you can factorize your alpha and your beta out. Okay, so factorize your alpha and your beta out. Okay? Okay, so you get these two terms. Can see? Okay, so when you separate them into two terms, okay, what is so good about this? So you can do the Z transform individually, okay, because you have simplified it. Okay, so where a and b are the constant it's just the coefficients. Okay, you can, so if it is just a coefficients, you can just take up. Okay, so then we look at the examples here. So the first one, Z transform of 4k minus 3 exponential to the power of negative k, right? So in this case, it can be written in this way, right? You have two terms. So the first term is Z transform 4k minus Z transform 3 exponential to the power of negative k. Okay, so in this case, you can bring the coefficient out. Okay, so basically you are solving Z transform of k and Z transform of exponential to the power of k. Okay, so Z transform of k, you get this, right? Z transform of k, you get Z over Z minus 1 square. Okay, so you just put it. Okay, the 4 you just copy, and then zk transform of k will be z over z minus 1 square. Okay, then you solve the first part. The second part will be exponential to the power of negative k. Okay, so we something look something like this, right? Okay, so in this case, your a is e, right? Your a for this term is e. Okay, so it will be z over z minus e exponential negative 1. Okay, e to the power of exponential negative 1. Okay, then for here, your term, okay, your term will be z more than 1. Okay, why you have z more than 1? Okay, because you have two terms, right? Okay, so you have this and this. Okay, for this condition, for this part here is z more than 1. For this part 1 is a certain number that more than 1. So everything, the minimum number of z will be 1 lah. Okay? Okay, so it will be z more than 1. Okay, at the back. Okay? Okay, guys? So that's why you have z more than 1 here. Okay, because of one term is z more than a, the other one is more than 1. Okay, A is of course more than 1. So you just stick to the minimum numbers. It will be Z more than 1. Okay. Okay, so if you have a constant number, if you want to do Z transform or a constant number, okay, so in this case, you know that Z transform of 1. Okay, so just now you have seen this, right? Z transform of 1 equals to Z over Z minus 1. Okay, so you bring the 3 multiplied by 1 out, right? So 3 is the coefficient. So you do Z transform of 1. Okay, then you just multiply the number 3 in. Okay, so for the terms, it will be Z more than 1. Okay, so you can scroll back. Okay, Z more than 1. Okay, okay, so far, okay? No problem, yeah? Okay, next. Z transform of 5k 2 to the power of k. Okay, so first of all, you know this is a coefficient. So you bring the 5 out. So now you are doing Z transform of k 2 to the power of k. Okay, but you look at here. I don't have k 2 to the power of k, right? Either I have this term, either I have this term. Okay, but for this term, I am having a to the power of k minus 1. Okay, so remember the previous techniques that we do, we expand it. Okay, we can expand it, or we can make the terms, okay, into the form that we want. Okay, so for here it's actually for 2k, I use pen. So 2k is actually equivalent to 2 multiplied by 2k minus 1, because 2 is 2 to the power of 1, right? So minus 1 plus 1 will be removed lah, right? So if you want to make it do the terms k minus 1, you can make it in this term. So it will be 2 multiplied by 2k minus 1. Okay, so you can see this term here. Got it? So they expand it so that the power will be k minus 1. Okay? So when the power is k minus 1, so you can see k 2k minus 1, right? So you get this term, correct or not? Okay, so meanwhile, when you get this term, you have coefficients of 2 lah. So the 2 you can bring out. So it will become a 10. 2 minus 2 multiplied by 5, you get a 10. And remaining with Z transform of k 2 to the power of k minus 1. Okay, then you can use this. Okay, so at the end, it will be 10 multiplied by Z over Z minus 2 to the power of 2. Okay, and Z more than A. So your A is 2, right? So Z more than 2. Okay. Okay. Okay, if no question, we can take a break. So then we come back with the first shift property. Okay. The break will be 7 minutes. So we come back by 7 p.m. Okay. Okay, can everyone hear me? Okay, so we continue with the property of Z transform, the second property. Okay, so just now the first property is just very straightforward. Okay, so all you need to do is to find out the terms, especially in this kind of conditions. Okay, you can separate them into two or three, right? Okay, and of course, in this type of conditions, you can pull out all the coefficients. Okay, and try to make the terms match with the theorems. Okay, so that you can get the all right, get your answer from by referring to the theorems. Okay, so the second property, okay, first shift property. Okay, so the shifting property is actually a delay or to shift to the right. Okay, time shift property. Okay, so this is just like what we have learned before this lah. So you have this. Okay, then it will be starting somewhere, right? So it shift. Okay, shift after, so it start after when time equals to zero. Okay, or k equals to zero. Okay, so it's like shifting away, right? So when it is a shifting, you have one more terms here. Okay, so you have these terms. Okay, so for this one, okay, when you do the Z transform, you will get this term. Okay, so you will get one more terms, which is 1 over Z, okay, with this to the power of this. Okay, so this is the shifted term lah. Okay, or you can say the shifted time. Okay, so let's say the shifting time is like k minus 3, so this one will be a 3 here. Okay, 1 over z to the power of 3, or z cube. Okay, remaining with the remaining terms for z transform. Okay, so where hk is a unit step sequence and k is a positive constant integer, the number of steps in the delay. Okay, so this is the original one. Okay, when xk minus k, okay, it will be shifted. Okay, the whole thing shifted. Okay, it's starting from somewhere lah. Okay, depends on the k lah. Okay, depends on a given k. Okay, then we look at the examples here. Okay, so given this, okay, z k minus 2, hk minus 2. Okay, so it will be equivalent to 1 over z to the power of k0, right? So k0 is 2 here. Okay, k0 is 2 here. Okay, so when you know that, okay, so this is just like when you're doing the Laplace transform, remember? So you have t, and then you convert to t minus a, right? So in this case, k you convert to k minus your numbers, right? So when you resolve this term, okay, when you resolve this term, you have remaining with z transform of k, of the term k. Okay, because of the 2 is already break out. Okay, so 1 over z to the power of z square lah. Okay, then the z transform of k, you get this. Okay, z over z minus 1 square. Okay, then you just do this. Okay, simplify it, you get 1 over z multiplied by z minus 1 square. Okay, okay, or you have this example. Okay, delta k minus 3. Okay, so delta k equals to 1. Okay, so you need to eliminate the minus 3, right? So in this case, the k0 is 3. So 1 over z to the power of 3 lah, or z cube. Okay, remaining with your z with the lambda k, sorry. Okay? Oh, sorry, delta k. Delta k. Okay, but the z transform of delta k, you get a 1, right? So you remain with 1 over z cube. Okay, okay, actually quite straightforward lah for the z transform. Okay, next, another example. Determine the z transform of the following sequence. Okay, so this is the given sequence. Okay, they didn't write out the terms. Okay, but they give you a sequence. Okay, so from here you can see the sequence started from 0, 0, 0, and it only come with 5 when after the third terms, right? So okay, so it's actually 0, 1, 2, 3. Okay, so this is the z care is this sequence. Okay, so z care equivalent to 0 when k is less than 3, right? Because 0, 1, 2, so k is less than 3. Okay, and it will be 5 over 2k minus 3 when 3 is when k is more than or equals to 3. Okay, because this is the third term, 4, 5, 6. Okay, but how you get this? Okay, let's say for this term is term number 3, right? So 3 minus 3 will be getting a 1, right? So sorry, 3 minus 3 you get a 0. Okay, so 5 over 1. Okay, so get back 5 lah. Okay, so the fourth term will be k minus 3. K at 4 minus 3, you get 1. So 2 to the power of 1. Okay, so it'll be 5 over 2. Okay, so you know how to form these expressions. Okay, according to the given sequence here. Okay. Okay, of course, the sequence given there, you must be able to form this. Okay. Okay, then you can write out the expressions. So because for k minus 3, you know that it's actually a shifting. Okay, it's a shifting sequence, right? So it'll be 5 over 2 to the power of k minus 3 h k minus 3. Okay, so this is the shifting part. Okay. Okay, so once you form this unit step sequence, you can start to do the Z transform. Okay, so in this case, you can see 5 is actually the coefficients, right? Okay, because you can get 1 over 2 k minus 3, right? So 5 is actually the coefficients. You can put a 5 out. Okay, so for this one, if you put a 5 out, you get 1 over 2 to the power of k minus 3. Okay, so it's also equivalent to 1 over 2 k minus 3. Okay. Okay, so you can get these terms here. Okay, then it will be coming with 2 terms lah. Okay. Okay, so the whole terms, you want to do the Z transform, okay, you refer to this. Now you know that your K0 equals to 3, right? So you can bring these K0 terms out. The K0 terms will be 1 over Z to the power of 3. So over here you have 1 over Z to the power of 3. Okay? Okay, so when you take out the K0 terms, you're remaining with your term with K only. So your term 1 over 2 and this k minus 3 become k. Okay? Okay? Then you just simply do the Z transform of this part. Okay, so Z transform of this part when you have an A to the power of k. So 1 over 2 is your A. Okay? So A equals to 1 over 2. Okay? So it will be Z over Z minus 1 over 2. Z over Z minus 1 over 2. Okay, then you just rearrange it. You will get 1 over 2, Z over 2, 2Z over 2Z minus 1, right? Then you just 2Z multiplied by 5, okay? But divide by over Z cube, right? So you simplify it, you will get 10 over Z square bracket 2Z minus 1. Okay, so in this case, just now we got it, A equals to 1 over 2. So Z more than A. Okay, so Z will be more than 1 over 2. Okay, so I'll give you some time to look at this. Property. Okay, second shift property. Okay, so this one, the second shift property will be shifting to the left. Okay, so you can see it will be minus n. Okay, so this one will be very complicated. Don't look at this first. Okay, we just look at here. Okay, so we know that, okay, z, okay, xz, okay, is equals to z with the sequence. Okay, so what is h? H is the unit step sequence, okay, when the k is a positive constant integer. Okay, so in particular, putting, okay, k0 is 1 and k equals k0 is 2. Okay, so you can look at these examples here. Okay, so okay, in the previous one, it will be k minus a numbers, right? So shifting to the left will be plus the number. Okay, so this is the difference. Okay, so you can look, you can take notes, okay, at the sign, okay, whether it's a plus or minus. Okay, the first thing. Okay, second things is, okay, for this one, if you want to z transform x k minus 1, okay, you can see it is actually, okay, okay, it's already been proven. Okay, you can be writing it into this form. Okay, so do this look similar to you? Okay, so this one you have learned in Laplace transform, right? It's actually similar to a Laplace transform. Okay, but this one is Z transform. Okay, so same, if you have Z plus 1, so you have two terms. If you have k plus 2, sorry, k plus 2, you have three terms. Okay, so the first term will be zxz minus z0 z. Okay, so z0 is the first term lah. Okay, the first term. Okay, so this one will be z square. Okay, when you have plus 2 z square x z, and you have first term multiplied by z square minus the second terms multiplied by z. Okay, okay, so this is the general formula lah. Okay, so but the k will be, k0 will be more than 0. Okay, it will be a positive terms. Okay, for k. Okay, so hence hk plus k0 will be equals to 1. Okay, okay, so you remember this part. Okay, so if you have k plus 3 also, you should be able to list it up. Okay, okay, according to this pattern. Okay, it's what I mean same with Laplace transform, it's just like the same concept with Laplace transform. Okay, it's not exactly the same. All right, so yeah, this one is for the Z transform. Okay, then we look at the example given. Okay, use the first SP to determine the Z transform of the causal sequence. Okay, YK. So this is the sequence given now, YK, defined by this. Okay, so you see, they say that when K is from 0 and less than 4 is a 0. So means that K0, K1, K2, K3 is 0. Right? So you have 1, 2, 3, 4, 0 here. Okay? So because this is a K0, until this one will be the K3. Correct or not? And this one, the following by K4. So K equals to 4 or more than 4 is 1. So you have 1, 1, 1, 1 until infinity. Okay, because they didn't say the maximum number. Okay. So firstly, you can list out the sequence. Okay. So far should be no problem, right, for a sequence. Okay, then okay, so this is the question is given. Okay, so when you do the Z transform of YK, okay, when you do the Z transform of YK, it will be equivalent to ZHK minus 4. Okay, so why minus 4? Because of this, the K terms. Okay, because after 4, only it will be 1, right? So HK minus 4. Okay, okay, when it's K minus 4, it will be 1 over Z to the power of 4. So 1 over Z to the power of 4. So remaining with 1, okay, because of 1. Okay, so Z transform of 1. Okay, then when you have Z transform of 1, so you will be able to get Z to the power of 4 multiplied by this, right? So Z over Z minus 1. Okay, then you simplify this one becomes 3. So you get 1 over Z cubed multiplied by Z minus 1. Okay, and Z is more than 1. Okay. Okay, if you have a question, you can raise your hand. Okay, or ask in the chat. Okay, so Z transform is just very straightforward. Okay. Okay, then we look at another example. Write down the sequence y when k plus 2 and use the first SP to determine the Z y k plus 2. Okay, so just now we know that, okay, this is same question now, 1 and continue with 2. Okay, so this is the original sequence, okay, but now they have plus 2. So the shift 2, okay, so the shift 2, okay, to the left, meaning that they are bringing from here. Okay, so the sequence, you can see the sequence is 0, 0, and followed by 1, 1. Okay, because they shift everything to the left. Okay, so this was the original one. So before that, it should your 0. Right, okay, so just now, before this, okay, it should be 0, 0, 0, 0, and then start with 1, 1, and etc. Right, so this is the previous sequence, right? Okay, but in this case, okay, in this one, they say to shift to the left for 2, right? So you bring everything to the left 2. Okay, so means from here is starting 1, right? So when you write the sequence, you write for sequence from here, the causal sequence, okay? So it should be starting from here, okay? So 1, 0, 2, 0, okay? So when it's 0, when it's k, is more than 0 and less than 2. Okay, and the third one will be 1, 1, 1. Okay, so it will be k more than 2 equals to 1. Okay, so this is what that means by C shift to the left. Okay, so k plus 2. Okay, by referring to the original sequence, okay, they will be missing lah. These two. Okay, so this is what you get here. Okay, this is what you get here, and also this one. Okay. Okay, then you do the Z transform. Okay, so when you do the Z transform is first shift property. Okay, okay, it should be because it's just one, right? So the terms will be one. So Z with H, so H minus 2. Sorry, H K minus 2. Okay, because you have this. Okay, so K minus 2. Okay, when it's K minus 2, 1 over Z to the power of 2, remaining with Z transform of 1. Okay, so Z transform of 1 will be Z over Z minus 1. Okay, so 1 over Z square, sorry, 1 over Z square, Z over Z minus 1. Okay, so cancel off, cancel off. Okay, so you get 1 over Z, Z minus 1, and Z more than 1. Okay. Okay, then you look at the third. Okay, it's still the same question. Okay, also use the second SP to determine Z, Y, K plus 1 and YK plus 2. Okay, so just now YK plus 2, you remove 2, 0, right? So this is your K plus 2. Okay, so if K plus 1, you will only remove 1, 0. So you have 3, 0 in front. Okay? Okay, so now you know how you get these two. Okay, then you use the second shift property. So the second shift property just now, we see this. This is the technique that I mentioned. Okay. Okay, so if it's just K plus 1, you just plug in this. Okay, so you will get, okay, so this one will be very confusing. Okay, so you can straight away jump here. So what you get? You will get Z, Z, X. Okay, so YZ, right? YZ. So this is the Z transform of your Y lah. Okay, minus Y0Z. Okay, so by referring to here. Okay. So after you get rewrite this, you know that Y0 is actually 0. Right? Y0 is actually 0. Okay, so it's just minus the 0. Okay, and then Z, 1 over okay, so this part, okay, so just now you have done Z transform of YK. Okay, so remember here, okay, you have done a Z transform of YK. So this is the terms 1 over Z cube, Z minus 1. Okay, so just plug in 1 over Z cube, Z minus 1. Okay, so just cancel off a V, Z over 2 here. So 1 over Z square, sorry, Z cube. Okay, 1 Z square, sorry, 1 over Z square, Z minus 1. Okay, so how you get this term? This term is from the first question. Okay, 1. Okay, this is 3. Okay, so from question 1 here. Okay, you get here. Okay, based on this question, it's still in the same question. Okay, so you have the Z transform of YK. Okay, if you don't have, if the question give you this, then you must find back. Okay, do your own here. Okay, do your Z transform of this YK. Okay, so not yk plus 1 or k plus 2 is yk. Okay, why is yk? Because when you use the second shift property, you know that this is how it formed. Okay, use Z transform of the second shift property, you will get this. Okay, so exactly the same thing, you just plug in here. Okay, then you do this part. Okay, this one you just follow the sequence. If y0 is 0, you just put 0. If a 1, you just put a 1. Okay, so this one is k plus 1. For k plus 2, you will get z square, z transform of yk minus y0 z square minus y1 z. Okay, so in this case, y0 and y1 both 0. Okay, okay, so when y0 and y1 both 0, so you just put in. Okay, so it should be z square, and then this one you just plug in from the previous answer. Okay, then you just simplify it. Okay, you'll get 1 over z minus 1. Okay, 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 then we proceed to the final property. Okay, so this final property is very, very straightforward. Okay, so you have z, okay, then you multiply by terms. Okay, so when you multiply by terms, it will be z over a, and in this case, you replace the z with z over a. Okay, so what that means by is you replace the z with z over a. Okay, so the previous one, after you do a Laplace transform, you'll get z x z, right? So this one will be x z over a. Okay, so of course when we look at this theorem, we cannot understand lah. Okay, so the proof is given here. Okay, but then we can go through the example. Okay, so this is the theorem. Okay, if you z transform ak x z, okay, you will get z transform of xk with your z replaced by z over a. Okay, so this is what that means. If you want to do z transform of ak xk, so previously you don't have this, right? You only have xk. Okay, so z xk, you will get z transform of xk, and your and your z will be replaced by z over a. Okay, so look at this question. Okay, so this one we have seen just now, sine ak, right? If you do z transform of sine ak, you get z sine alpha over z square minus 2z cos alpha plus 1. Okay, so in this case, okay, with the multiplication terms, you know that you need to replace the z with z. Z you replace with z over 3. Okay, z over 3 because the terms is 3 here. Okay, okay, so in this case you have the first z sine a, so it will be z over 3 sine a over, it will be z square, right? So z over 3 square minus, here you have one more z term, so z over 3, 2z over 3 cos a plus 1. Okay, so in this case, because you replace z with z over 3, right? So z over 3 more than 1. Okay, the conditions z over 3 more than 1. Okay, then you just rearrange this. Okay, rearrange here, everything multiplied by 3 lah. Right, rearrange this, then you get 3z sine a over z square minus 6z cos a plus 9. Okay, and then over here you rearrange it because you want it to be in the form in terms of z. Okay, so z will be more than 3. Okay, so for the multiplication property is very straightforward. Okay, then you look at the final example of the day. Okay, So similar questions lah, okay? But in this case, it will be another terms. Okay, so we look at this example. Okay, so exponential to the power of 2k. So this is the terms, right? This is the term. So you know that you need to replace z to z over exponential negative 2. Okay, z over exponential negative 2, this the whole terms. Okay, so because a in this case is exponential negative 2. Okay, okay, then you just follow lah the cos. Okay, the theorem of z transform for cos ak. Okay, so you get z multiplied by z minus cos a. So z will be ez. Okay, so this one you just rearrange it. Okay, or you just want to remain this term also can lah. When but after you put in, you still rearrange it. Okay, because negative 2. Okay, so if negative 2 also, sorry, 1 over exponential to the power of negative 2 will be exponential to the power of 2 lah. Okay, so e square z. Okay, so the z you replace with exponential square z. This z replace with exponential square z minus cos a, and then your z square exponential square z and the whole thing square, right? So you get exponential to the power of 4 z square. Okay, minus 2, and then you have again exponential square z. Okay, cos a plus 1. Okay, and finally your z will be more than these terms. Okay, because you replace your z with this, so it will be okay z more than exponential negative 2. Okay, okay, so that's it. Okay, so what is the main point for these chapters will be you need to know how to do the z transform. Okay, and you need to know for these 4 properties. That's it. Okay, these 4 properties, that's it. Okay, so multiplication and the linear is very straightforward. Okay, then what you need to do is to do more exercise for first shift property and second shift property lah. Okay, basically it's just to follow their theorem. Okay, any question for this? No question, huh? Okay, I suppose the z transform will be much more easier lah. Okay. Okay, so if no question, I think that's all for today. So for those have question, you can stay in the chat.